It is my great honor to present the first Frontier of Science Award winner, Ned Scotts from Rice University, and he will talk to us about Kakeya sets in R3. Let's welcome him.
Um, okay, it's a great honor and pleasure to be here, and I'd like, of course, to thank the prize committee and the organizers for inviting me. I'm going to be talking about joint work with Josh Zoll about Kakeya sets in R3. Um, oops, my pointer is not working. It was working 5 minutes ago, but oh, there we go. Okay. So a Kakeya set, also called a Bezukovich set, is a compact set in some Rn. We'll focus on R3, which contains a unit line segment in every direction. So these sets are named after the Japanese mathematician Soichi Kakeya, who asked the following question. What is the minimum area needed to continuously rotate, this is in 2 dimensions in the plane, to continuously rotate a needle of unit length 180 degrees in the plane? Bezukovich answered this question by showing that it's possible to construct such a set with arbitrarily small area, and furthermore, that it's possible to construct a Kakeya set with Lebesgue measure 0. So Kakeya's original question was a little bit more delicate because he wanted to really continuously rotate the needle. Whereas to have a Kakeya set, you just need to have the position of the needle without worrying about any continuity. And so when you take away this restriction about continuity, you're able to get this with measure 0. Okay. So Bezukovich demonstrated that there exist Kakeya sets with Lebesgue measure 0, but that's not as small as a set can be. So you could ask yourself, what can you say about the dimension of a Kakeya set? And there's a conjecture that asserts that the dimension has to be full. And of course, there are different notions of dimension. Everywhere where I say Minkowski, I mean upper Minkowski, and I think probably this is the only slide where I messed it up. But the conjecture is that every Kakeya set in Rn has Minkowski and Hausdorff dimension n. So there's this set of Bezukovich that has measure 0 in the plane, but it has dimension 2, both Hausdorff and Minkowski dimension 2. And the Kakeya conjecture was proved by Davies for n equals 2, but it remains open in 3 and higher dimensions. And today I'm mostly going to be talking about the situation in 3 dimensions. So I'm now going to state results in R3. Wolf, this was published 1995, proved that Kakeya sets in R3 must have Minkowski and Hausdorff dimension at least 5-halves. And we're going to talk about where this estimate of 5-halves came from. And beyond that, only small improvements are known. So with Isabella Laba and Terry Tao, we showed in 2000 that the upper Minkowski dimension of Kakeya sets must be at least 5-halves, plus C0, where C0 is a small positive constant. I think that when we published this paper, our claim about C0 was that it was at least 10 to the minus 10. But I think various things can be done a little bit slicker, and uh, by now, um, by now that constant is a little bit bigger. Um, but today I'm going to talk about my 2019 paper with Josh Zoll. This is the prize paper, and the result is that the Hausdorff dimension of Kakeya sets in R3 must be at least 5/2 plus a positive constant, and this positive constant is even smaller. I don't want to venture what that constant is. It roughly has to do with the number of lines in the paper. So at each line in the paper, you lose something in the constant. Okay. Uh, More recently, Hong Wang and Josh Zoll have shown the Kakeya conjecture under a structural assumption on Kakeya sets, which is called stickiness. And indeed, they've shown that a Kakeya set in R3 must have full Aswad dimension. Basically, it means that there is some pair of scales so that when you thicken at the smaller scale, you have to come close to filling up a ball at the larger scale. But that's a much weaker result uh, than than solving the full conjecture. So I want to say something about how this is related uh, to these two results. The notion of stickiness was first defined in this paper, and basically the idea of both papers is that sets that are very close to tight for Wolff's estimate have a lot of rigidity. One has a lot of information about what such Kakeya sets look like. And stickiness was a property that was guaranteed for such sets in the upper Minkowski dimension version of the problem, but was not guaranteed for Hausdorff dimension, which is why it took another 2 decades. And so, in one sense, what is new in this result that was not known here, even though the results look quite similar, is that we had to deal, and we were able to deal with a non-sticky case. And I'll say more about what is meant by stickiness a little later.
Is it like a doubling property? Do you think of it that way?
It's a kind of self-similarity property. Okay, I will tell you now what stickiness is. So much of this subject and much of what I'm going to say later in the talk is about slight thickenings of the problem. So I've been talking about Kakeya sets that have a unit line segment in every direction. But if I thicken everything by a scale delta, I get a delta tube. And stickiness has to do with how things change when you change the scale. So a delta tube I'm going to call a thin tube. And very often when I have a delta tube, I'd like to think about the delta to the 1/2 tube which surrounds it. And so this is my thin tube. And this is what I'm going to call a fat tube. And the Kakeya set is sticky if most of the thin tubes, which have direction within the directions allowed by the fat tube, are contained in the same fat tube. So if you have stickiness, roughly speaking, you have one thin tube in each of a delta separated set of directions, and you have one fat tube in each of a delta to the 1/2 separated set of directions. But if you don't have stickiness, you have a lot more fat tubes, which have fewer thin tubes in them. And that's the kind of difficult situation that that our paper deals with. Yes, it's really the first one was an easier problem. Okay. um, yeah. All right, good. Um, okay. Sorry, now I'm going in the wrong direction of the slides. That's bad. Okay, so I'm just restating this result. And the result is very technical, so you will all be disappointed. I will not give a rigorous proof of the result in this talk, but the purpose is to give some of the ideas of the proof and to give those ideas some context. So here I'm saying what I really drew on the board over there, that a usual first step is to discretize at some scale delta. And then when we do that, we are talking about only a finite number of delta tubes. We can count intersections between them, and we can generally borrow ideas from incidence geometry. The problem becomes a problem about counting. So now I want to spend one slide talking about definitions of dimension, which is a slightly technical subject, but a compact set K has upper Minkowski dimension at most D if for every epsilon greater than 0 and every sufficiently small delta greater than 0, which I should have pointed out is at this point allowed to depend on epsilon. So we can cover the set by at most 1 over delta to the d plus epsilon many delta balls. So when we are studying Minkowski dimension, there is one delta, and we are asking how efficiently can we cover the set by delta balls. And now for Hausdorff dimension, it's a little bit more complicated. So one defines a Hausdorff measure as the infimum of coverings of the set by balls of radius at most delta. And so then for each ball, one takes the radius and one takes its power d. And really, if I had prepared these slides properly, I would have named the Hausdorff dimension, the Hausdorff measure, the d-dimensional Hausdorff measure of k is this quantity. And then you take the infimum over d's for which that quantity is 0. But the thing that I really want you to pay attention to for the rest of this talk is the difference between upper Minkowski dimension and Hausdorff dimension. So for upper Minkowski dimension, we were dealing with coverings by balls of radius delta. There was one fixed delta that we would look at a time, whereas for Hausdorff dimension, you're looking at efficient coverings by balls of various radii, because this infimum is taken over all coverings by balls of radius at most delta. And so there's going to be some slightly technical descriptions of parts of delta tubes, which will basically signify the part of the delta tube that's covered by balls of radius delta in the efficient covering. So let me now say that.
Is it philosophically correct to say that you want stickiness implies Hausdorff dimension?
No, no. We do not have an implication to stickiness, so we can't get anything from from stickiness. Here, we're going to get an unconditional improvement over 5/2. In fact, it turns out that given stickiness, Wang and Zoll are able to show you actually have dimension 3. But stickiness is kind of sticky. It's difficult to get. Okay, good. I keep wanting to make sure I'm not getting behind on time, but I'm not. So so I've defined a delta tube already, and I'm going to use calligraphic T to denote a set of delta tubes. We define the direction of a delta tube to be the direction of its coaxial line, meaning the line that's in the center, and we say a set of delta tubes is direction separated if the tubes point in delta separated directions. And in what follows, it will be useful to consider sets of delta tubes along with distinguished subsets of each tube. So the full structure that we study is calligraphic T, which is a set of tubes, together with Y, which is a function that when you feed it each one of the tubes gives you a subset of the tube. And the way you should think about this is that it's the part of the tube that's efficiently covered at scale delta. And so here I've made a bunch of notation, and what this notation is for the combinatorial, or if you like, geometric structure that you're studying when at a particular scale, when you're studying the problem of bounding below the Hausdorff dimension of a set. So the idea here is that Hausdorff dimension comes from efficient covering by balls of many scales, but at least some of those scales actually take significant part in the covering, and you pick a scale that does, and what you do is you've thrown away maybe most of the tube, but there's a significant part of each tube that you've kept, and that's y of t. Okay, good. Observe that any delta tube, for some reason I'm still in Rn, has volume delta to the n minus 1, right? There's one long direction of length 1, and there are n minus 1 short directions of length delta. And the maximum cardinality of a delta separated, of a set of delta tubes with delta separated directions is roughly delta to the 1 minus n. And so if I do this, if I take the sum of the measures of all of the shadings of the tubes, y of t is called the shading of the tube because I think of it as the part of the tube that I'm looking at, so I've shaded it. Then the total measure there is at most a constant. I want to say at most 1, and I want to throw away all my constants, but basically because it's bounded by delta to the n minus 1 times delta to the 1 minus n. And we're interested in the case where I've shaded a significantly large part of the tube. So we always have this inequality that the sum of the measures of the shadings is less than constant, but we're interested in the case where this inequality is almost tight. And what I really mean is that there's a lower bound here with, at worst, some delta to a very small power. So such a shading is going to be called nearly maximal. And one advantage, okay, so this is just another paragraph that says the same thing as I've been saying, which is the advantage of doing this is that our goal is to do counting, and one of the ways we can do counting here is that we're basically trying to find lower bounds for the measure of the union of the shaded parts. Okay, good. Tom Wolfe proved that the Hausdorff dimension of a Kakeya set in Rn is at least n plus 2 over 2, and when n is equal to 3, that comes out to 5/2. And this will amount to an estimate of this form. I have some nearly maximal shading of a set of tubes in R3, and I'd like to know that it is always the case that the measure of the union of the shadings is at least delta to the 1/2 plus epsilon. And the way you should think about this is that the epsilon is whatever I threw away when I said here nearly maximal shading, or something that just depends on what I threw away. And that the 1/2 corresponds to dimension 5/2. And what I am going to do next is that I'm going to give a heuristic version of Wolff's argument. You guys should get very scared every time I say something is heuristic, because it means some lies are sneaking into what I'm saying. But the heuristic for Tom Wolff's argument is very robust, and so it survives quite well against my lies. So here's kind of the main idea of Tom Wolff's argument. So given nearly maximal shading, we define for each tube, there's a misprint here. We define for each tube the hairbrush of T, which is the union over T prime that intersect T, and this should have said Y of T prime. My apologies. So you let me draw a picture. So here is T, and the hairbrush of T, so this is T, and this is one of the T primes, and the T prime is shaded. So these shaded areas are the Y of T prime, and you
Why is it called airbrush?
That is a little confusing, but you could imagine that this T, which is the stem, is what you're kind of holding the hairbrush by, and you're going to use it to brush your hair. And the tubes that are coming out of T are the bristles of the brush. So that's roughly the idea. Okay, so I hope it's clear what. So in the current setting we're in, we're just going to take them as given to us. But once again, the way I choose them is that I have this set whose Hausdorff dimension I am trying to work out. And so I cover it with balls of different sizes, and I pick a fixed size that covers a lot of it. And then for each line, I shade the balls of the right radius. Okay, thank you. All right. So those T prime which participate in this union are called the tubes of the hairbrush. And the main idea, I like to say that the main idea of Wolff's argument is that every triangle lies in a plane. So it's a very important idea. I would claim this was, in 1995, this was the first time that idea was used in the Kakeya problem. And so the point is that if, and okay, here I'm cheating a little because I'm pretending that tubes are lines in this next drawing. But if I have two lines that are intersecting, this is supposed to be T, and these are different T primes. And if I have two lines that are intersecting T and intersect each other, they have to live in a plane. And so it's decomposing the hairbrush into these planes, which is kind of the key idea of Wolff. And so this is the type of heuristic that I will sometimes force you to endure, which is that I'm going to really treat my delta tubes as if they're lines. And then what I want to say is that this hairbrush kind of I'm not very good at drawing in R3, but there's a one-dimensional family of planes in R3 that contain this line, and the hairbrush is subdivided into different planes, and at least far away from this tube, even the thickenings of these planes are disjoint, and so the tubes that lie in different planes essentially don't interact. And moreover, the tubes that lie in a given plane don't interact very much. That's something that I haven't explained, but it's part of this result of Davies, which gives the Kakeya problem in R2. R2 is just too tight for there to be much interaction between tubes. So the upshot is that all of the tubes in a hairbrush H of T are essentially disjoint. So now in the next slide, I'm going to explain how we get from that to 5/2. Okay, so now I'm saying this again, that the measure of the hairbrush is essentially the same as the sum of the measures of the individual shadings of tubes in the hairbrush. Okay, so here comes a heuristic version of Wolff's estimate. In order for everything I'm saying to be true, you have to imagine various things like the diameter of intersections of two tubes is delta, which is in fact only true for tubes which intersect at large angle. But it turns out that the large angle intersections dominate and are the things one should pay attention to. And what I said, the last line I say in this paragraph is that each of these simplifying assumptions is inessential, meaning that even though what's going to be written on this slide isn't perfectly rigorous, there really is an argument that's of the form of what's going to be written in this slide. And now the next step is kind of, oh, sorry, that was already written here. I'm not successfully reading my slide. We'll also assume that at each point of the union of tubes, exactly mu tubes intersect, and I really mean mu shadings of tubes. And why should that be? I mean, you go from one point to the next, at one point maybe 1 million tubes intersect, at another point a billion tubes intersect. But the answer is that you sort of sort them. This is a process called dyadic pigeonholing. You find a number mu that reflects that for a large part of the set, between mu and 2 mu tubes are intersecting at every point. So I'm going to pretend that at every point the same number of tubes are intersecting, and that number of tubes that is intersecting is going to be called mu. And from that, we're going to get two estimates for the union of the tubes. One estimate is that we just take the sum of the measures and we divide by mu, and it has to be at least that because each point is covered only mu times. That's why we get to divide by mu. But the second estimate involves how big the hairbrushes are. And each hairbrush should be of size, should have at least mu delta to the -1 tubes. And the reason for that is that there are basically 1/delta balls where tubes can intersect. I'm only counting tubes that intersect with large angle. And each one of these has mu tubes. And so altogether, you have mu delta to the -1 tubes. And those tubes, because it's a hairbrush and because they separate into planes and because planes are tame, are essentially disjoint. And so you multiply mu delta to the -1 by delta squared, and you get a lower bound of delta mu. So we have these two different lower bounds. When we have two different lower bounds, it means we have an enemy mu. The enemy mu is where the lower bounds match, and they clearly match when you have mu being delta to the -1/2. And when mu is delta to the -1/2, it gives you the estimate that you want. It gives you the 5/2 dimensional estimate. Okay. And that's what I say in the last line of this slide. Okay. So the key idea in Wolff's theorem is that unless the Kakeya set has dimension at least 5/2, then the typical hairbrush has dimension at least 5/2. And since the hairbrush is a subset of the Kakeya set, that's a contradiction. But now, if you want to imagine that Wolff's result is sharp, if you want to imagine that there's really a Kakeya set of dimension 5/2, it has to actually be a hairbrush. And all of the hairbrushes have to be the same, roughly. I mean, they don't have to be perfectly the same because I can lose a delta to the epsilon somewhere. But typically, there has to be very large intersection between any two hairbrushes. And you start to think about that, and you wonder, can this happen at all? And when Laba and Tao and I were initially working on this upper Minkowski dimension paper, this was really our initial point of view, that it must be very, very hard for hairbrushes to completely overlap each other, and this should be the way to gain at least a small improvement over Wolff's estimate. And this is much harder than it sounds. Even for the 2000 result, even for the upper Minkowski dimension result, this was much harder than it sounded. And the reason it was hard is that there are some near miss examples. There are things that we can describe that are not exactly Kakeya sets in R3, but have some of the features of Kakeya sets in R3 where this seems to fail. And the way to prove a theorem is that you show that the near miss can't actually can't actually exist as a Kakeya set. And the reason that the Hausdorff dimension problem is harder than the upper Minkowski dimension problem is that there's an extra near-miss example which we found. Well, I'm going to tell you what they are. I'm going to tell you what they are, but depending on what you mean, where do they come from? Oh, well, I would say that algebraic varieties play a much greater role than you would expect in producing these. So I could say they come from algebraic geometry. Oh, okay. But in fact, the extent to which that's true will be kind of obvious in my next few slides, which are close to the last slides. I have about 10 minutes left, right? Okay, good. Okay, so one near-miss example we call the Heisenberg group. So this is a 5 real dimensional set in C3. So the complex numbers we think of as 2-dimensional over the reals. And it is exactly this set, the set where the imaginary part of Z is equal to the imaginary part of X times Y bar, where X, Y, Z are the coordinates in C3. Okay, I should say something about why it's the Heisenberg group. It really has a natural group action as the 5-dimensional Heisenberg group. It contains a 2-dimensional set of complex lines. So from the complex point of view, the Heisenberg group is 5-halves dimensional, right? It's 5-halves dimensional over the complex numbers. And it contains a 2-dimensional set of complex lines, which is like being a Kakeya set. You're a Kakeya set when you have a line in every direction. I'm not promising you these lines are in every direction. In fact, they're not. But there is a 2-dimensional set of these lines. And the lines they're not in distinct directions, but they do satisfy something called the Wolf axioms, which means there's not more than a 1-dimensional set of these lines in any 2 complex dimensional plane. And of course, they're not a real object, they're a complex one. And for our purposes, the complex numbers are really different from the real numbers in that the complex numbers have a half-dimensional subfield, the reals. But the real numbers do not have a half-dimensional subfield. Something that, believe it or not, was still an open problem at the time, sorry, not a field, but a half-dimensional, even a half-dimensional subring. Having a half-dimensional subring in the reals was still an open problem at the time of the paper with Laba and Tao, and we actually slightly sidestepped this when we solved it. So what we so an object like the Heisenberg group over the reals can be ruled out using Bourgain's discretized sum product theorem, which among other things rules out half-dimensional rings in the reals. But that theorem was not yet known at the time of the paper with Laba and Tao. And so we actually dealt with this enemy example. So the way our paper worked was that we said a Kakeya set had many, many properties. If it was close to dimension 5-halves in upper Minkowski, it had stickiness, it had something called graininess and something called planiness, which I'm not going to talk about. All of these properties forced it in a very strong way to really look like this. And then we were able to show from the strong way in which it looked like that that the directions of the lines were not really different, so it wasn't really a Kakeya set. That was how the 2000 paper worked. But it was all based on this Heisenberg group example. I guess this frame is not very necessary. It's all history. There doesn't have to be a metric. Oh, what do you mean? Okay, but none of this, mentions has to touch the metric. No. We are in R3. We're in R3. We want to know, is there a Kakeya set in R3? And if there is, in upper Minkowski dimension of dimension 5/2, then it's forced to look like this Heisenberg group thing, and it doesn't really have anything to do with the metric in the Heisenberg group. Okay, sorry. Do I still have 5 minutes? I need about 5 minutes. 6. Okay, awesome. Okay, so now what I'm going to describe is kind of the near miss example that shows up in the non-sticky case. And in fact, I think I want to mention maybe one other heuristic that I've avoided because it's sort of horribly unhelpful because of the way that it fails. But if you are in R3 and you have 4 lines in general position, there are exactly 2 lines that intersect all 4. That's a terrible picture of it, but that's a famous fact from enumerative geometry. And one thing I want to say about that is that suggests to you that if you have a 5/2 dimensional Kakeya set and somebody just hands you a half-dimensional set of the lines, from that half-dimensional set of the lines, you should be able to generate the entire Kakeya set by just taking all 4 tuples and taking the lines that intersect all 4, and those lines essentially all have to be in it. So that's a kind of very strong rigidity. And the problem with that heuristic is that it's a totally bad heuristic. And I want to explain why it's a bad heuristic. What's bad about this heuristic? So when you start with 3 lines in general position, then the set of all the lines that intersect them are one ruling of a doubly ruled surface. And it's everything I'm saying is true for lines, but is not at all so true for delta tubes. And so if my 3 lines were properly far apart in general position, it still would be the case that the delta thickening of this doubly ruled surface is divided into a ruling of delta tubes. But now if I take, so those are my 3 lines, and now if I take my 4th line, if my 4th line intersects the doubly ruled surface transversely, then everything would work, then my heuristic would be fine. But there's nothing to stop the 4th line from being tangent, from being or nearly tangent. And it turns out that the kind of enemy case that's missing, the near miss example, involves a lot of tangencies, that there's a parameter for how tangent you expect tubes to be to reguli. Reguli is an old-fashioned name for doubly ruled surface. And that parameter is exactly a parameter that measures stickiness. And so so there's a 4-dimensional set of lines. If we parameterize the lines in R3 as AB0 plus TCD1, this anti-sticky near miss has a three-dimensional set of tubes, and it's precisely those tubes for which AD minus BC equals 1. It's a quadratic family of tubes. This is a description of the fat tubes, of the delta to the 1/2 tubes. And that's why we call it the SL2 example, because anytime you see AD minus BC equals 1, that's SL2. And now I should tell you what is inside each fat tube. So inside each fat tube there's a three-dimensional set of fat tubes, so there's only inside a one-dimensional set of thin tubes, and the one-dimensional set of thin tubes that are in here are what we call a regulus strip. So you take a doubly ruled surface and you cut off a delta to the 1/2 strip of it, and the tubes that are inside the fat tube are an interval of size delta to the 1/2 in the ruling of the regulus. Okay, and I must have written that on these slides. The union of delta tubes which appear in a single delta to the 1/2 tube are a regulus strip, and in order for this to be a 5/2 dimensional Kakeya set, it's necessary for the regulus strips of associated to any two intersecting delta to the 1/2 tubes to be tangent in the delta to the 1/2 cube of intersection. So you have these fat tubes, which are a very large and completely well-defined set of fat tubes, and then each fat tube comes with a regulus strip that goes all along the fat tube, and the two regulus strips of any two intersecting fat tubes have to intersect tangently at the intersection of the fat tubes. So that's essentially the near miss example. Anything else essentially gets beaten by Heisenberg group type methods. And it turns out to be possible to rule out this behavior using arguments that are related to the Simretti-Trotter point line incidence theorem. And I think my last paragraph is again a statement that this is a kind of extreme anti-sticky example where the set of fat tubes is three-dimensional. If the set of fat tubes is any less in a near example, then there might be some regulus strips, but they aren't quite delta to the 1/2 wide, and so what you have is some picture where each fat tube has some pieces of strips, and the interaction between them violates Bourgain discretized sum product theorem. Okay, well, at this point, I've kind of completely failed to give you the proof, but I've at least hopefully told you what are the ideas that are involved in the proof. So I think I'll stop here.
There are any questions?
People study the diameter. Is the diameter of a Kakeya set bounded?
Where I think somewhere when I defined Kakeya set, I required it to be compact.
Oh, so it's compact.
Yes. So
Okay.
so that is purely to avoid cases where I'm not where I'm making some error by requiring Hausdorff measure to be finite.
How small can you make the diameter?
Well, the diameter has to be at least one.
Yes.
Um,
I can
and
prove that.
uh, and
Nobody cares about upper
I don't.
bound.
I mean, I care about whether there are any low-dimensional Kakeya sets, but we don't know that there are because we hope the Kakeya conjecture is true. But for instance, if I wanted the smallest diameter Kakeya set I could have, I would just take a ball, right? And the ball has diameter 1.
Oh, I see. Okay.
I mean, it's a stupid Kakeya set because it's not, you know,
And
they're all intersecting at the
so
center.
these problems are open for Besikovich or
Um, it's the same. It's just it's synonymous.
oh, it's synonymous. I thought there was a delicate difference between requiring continuously.
Yeah. That was that's no part of what I'm talking about. So what I've been talking about the whole lecture
Assumes
are
the
Kakeya
continuum.
set. No continuum. No,
Oh, no
no.
continuum.
You just have a set which contains a unit line segment in every direction.
Okay.
Other questions, please.
Does the assumption of alpha regularity or something like that help? I think there are people that are trying to argue under that assumption.
Yes. So for well, so Furstenberg, there's this Furstenberg set problem which very recently was solved kind of independently, unconditionally. But for a long time, people were making progress when they had exact Alfors regularity. But it's a somehow slightly unnatural condition here because what we're after is really a dimensional result. So we allow delta to the epsilon losses, and when you talk about exactly Alfors David regular, usually that's with strong constants without any delta to the epsilons, and so it's just somehow it's a little bit too strong a condition.
Okay. And so you said also that the Minkowski-Kakeya conjecture was open in dimension 3, right?
It's still open in dimension 3.
Stickiness doesn't
Stickiness,
help,
no. If you had stickiness, it would be fine. However, the argument that we gave that allowed us to use stickiness was tied to dimension 5-halves. It was because we were trying to perturb dimension 5-halves that we had stickiness. One doesn't have stickiness unconditionally for Minkowski dimension. Yes.
Thanks.
Questions, Igang?
Can you give me an example of a Kakeya set of Hausdorff dimension strictly less than n? I even can't think of.
Can I give you an example of a Kakeya set of Hausdorff dimension in Rn strictly less than n? That's your question?
Yes.
The answer is no, I cannot, because there's a conjecture that says that there's no such thing, but I do not know how to prove that conjecture.
Other question? Okay.
Thanks for your speech, and I'm a bit curious about how you can generalize the argument you use here to, for example, higher dimension cases. For example, in 4 dimension, can we do similar things and rule out some special
four
case?
dimensions, well, in 4 dimensions, first of all, sorry, no, that goes the wrong way. In 4 dimensions, there are better arguments. So in 4 dimensions, so Wolff's argument gives dimension 3, gives lower bound 3. And there are arguments that do not use discretized, Bourgain discretized sum product theorem that give you improvements over 3. And morally, the reason is that you do not necessarily see some product theory until you get to 3.5. Unfortunately, the lower bounds that we have in dimension 4 are not that strong. They're around 3.1. So there are arguments to give 3.1, and they have a somewhat different form than what I'm saying here. That was not what I was supposed to talk about because it's not the prize-winning paper. It's some other paper.
Thank you.
But okay.
Other questions, please.
So you mentioned that the method you used to prove the theorem was to basically rule out the bad examples, like the near miss examples. So
Yes.
how do you know that that's covers all the near misses? I guess, like, is there?
Well, that's the point. I didn't give the argument that these were all the near misses, but that is definitely part of the argument. The argument is that if you have a near miss, either it violates discretized Bourgain's sum product theorem, which means that hiding inside of it is a kind of Heisenberg group, or else it has to be of this form that it consists of a three-dimensional set of fat tubes with a regulus strip in each one, so that the fat tubes are essentially a quadratic surface of fat tubes, and that each two regulus strips in intersecting fat tubes are tangent. And this is impossible due to an extremal combinatorial argument, which I have not given.
Thank you.
Sure.
Are there any known relationships between Kakeya set and the Kakeya set in the original definition of Kakeya? So for instance, is it true that for any Kakeya set, if I take a delta neighborhood with an arbitrarily small delta, I get a Kakeya set that is that verifies Kakeya's definition continuous?
I don't know that. No. So the main relation is that when Bezukovich defined his set, which was by a fractal procedure, you take a triangle and you cut it into two triangles that you move over, and each of those two triangles you cut into two triangles. When he did that, he got something that could actually touch Kakeya's original question. So he could rotate through that structure, but in most future work, the subject was really only about sets that contain a unit line segment in every direction. One of the reasons for that is that since the kind of origin of the subject has become more tied to Fourier analysis. So in the 1970s, Charlie Pfefferman used Kakeya sets to prove unboundedness of the disk multiplier in every LP other than 2. And many of the motivations for studying this problem are related to that. There's a Fourier analytic problem, the restriction problem, where the restriction problem implies the non-existence of these sets. And so the motive is really to understand what effects on Fourier analysis will such sets have. And so it's not really very important to worry about how you move around in the sets, which was what Kakeya was interested in.
Thank you.
Sure, sorry.
Other questions, please? Okay, if there are no other questions, let's thank our speaker again. So we will resume in